Okay, I think we can make a start. So just before we start, as a quick show of hands, can I get can you raise your hands if you're from the energy sector? All right, it's about 5 of you guys. Okay, so I wanted to put a bit of context as to our talk. So I want to talk a little bit about energy, and then we'll talk about AWS afterwards. So a little bit of introduction, if we get the clicker going.
That's really hard.
No. No. So okay. If you could help me, next slide. So a bit of introduction. My name's Pubadu Abayasiri. Everyone calls me Pubs. I'm from CLP Innovation. So I run the digital business within CLP Innovation, which incubates and launches new services for our customers. And I've got my colleague here, Dee.
My name is Dee Lu. People call me Dee. I'm head of technology from the digital product team, also from CLP Innovation.
So for the next 35 minutes or so, what we wanted to do was tell you a little bit of background about who we are at CLP, why we launched this digital business, which we call Smart Energy Connect, and then also go under the hood and tell you about the different types of services that we leverage, and also some of the hard lessons that we've learned. So over the years or so, we've figured out how to manage our operations and then reduce our costs as well. So we figured out how to save several thousands of dollars on expenses on licenses, people, and also AWS costs as well, which Dee will get into. So a little bit about us. So CLP, it's an energy company. We're headquartered in Hong Kong, founded in 1901, so we've got quite a lot of history there. We've got about a market cap of around 30 billion US. So our footprint, although headquartered in Hong Kong, we've also got presence in India, China, and Australia as well. The types of generation assets, so we've got traditional assets such as coal, but a growing fleet of renewables. So solar farms and wind farms, which is quite an interesting set of assets. And then in terms of customers, we've got around 5 million customers that we directly engage with, and then indirectly through other countries as well. The energy sector has been fairly dormant for many, many years, but over the last 10 years, it's become super interesting. So some of the things that have been happening is that you've got the abundance of solar. So solar is becoming a lot more affordable and a lot more efficient. Wind turbines is becoming a lot more prevalent as well. Energy storage, it's a really interesting thing there, which is becoming a lot more, the economics are working out a lot more. And that does really funny things for our operations. And then electric vehicles, you've all seen the abundance of Teslas and so forth. There's interesting things that happen when you have all these electric vehicles which are connected to the grid. So the equivalent, one electric vehicle would consume the amount of energy that 2 houses would consume. And then the other one, the last picture you've got there is of a smart building. Smart buildings are really interesting because a lot of the buildings that were designed decades ago, they weren't designed in a very, very efficient way. So you've got a lot of retrofit happening. So these are all really fantastic things that are happening. So what's the challenge? Like, what's the problem that's there? Well, if you think about a utility and the types of assets that are there, so power lines, substations, power plants, they usually last for 20, 30, 40, 50 years. So when these were deployed many decades ago, these kind of innovations weren't available. So you've got this aging infrastructure that was developed at a time where things like these kind of innovations weren't taken into account. So how do you make sure you can accommodate these kind of things without ripping out all that infrastructure? Because it's way too expensive to do that. And that's kind of the problems that we try and deal with under innovation. So this is a typical value chain for a utility. On the far left-hand side, you've got a power plant that needs to generate the right amount of electricity, sends it through these big transmission towers, and then sends it through what we call a distribution network. And what that is the local power lines that you see in a city. Then on the far right-hand side, you've got the humble resident that's going to be consuming that electricity. So what tends to happen is that what you need to do is predict how much energy a consumer is going to use, and then make sure you generate the right amount of power in the power plant. So in the past, it hasn't been too difficult because the way that you predict how much a customer needs is you look at their historical profile, and then you look at the forecasted weather, and you can get some pretty accurate predictions of how much energy is required. So you can configure the power plant to make just the right amount. But what's happening now is all of those different innovations that we spoke about. So if we look at this a little bit closely, on the far right, you've again got that humble resident, but on the top of their roof, you've got a solar panel. So that solar generation, it's happening locally within that customer. So the customer doesn't need all the power from the power plant. The two icons at the top, you've got renewable energy there. So you've got wind and solar. Again, that's kind of injecting that generation within the network, but it's happening at very intermittent times. At the bottom there, you've got electric vehicles, which has a spike of energy usage at times, and then you've got energy storage there as well, where you can store power at cheap periods, and then when there is a peak usage, you can discharge that battery. And all of that is happening within that network towards the customer side. So how does a power plant figure out how much energy is required when you've got all of this flux happening out there? So getting that visibility is really important. So it's no longer just a one-way communication. You need to understand the traffic on both sides. So having the right set of visibility, getting the right streams of data, and getting a real-time view is really, really important. The other point is that on that resident side, that's just an example of a home. But it gets incredibly more complex if you look at a building, because buildings are going through these energy efficiency cycles too. So what you would predict how much a building requires is no longer the case anymore because there's all these optimizations happening. So an example that we can walk through is that suppose you've got a large commercial building. So on top of that commercial building, what you can do now is put a rooftop solar there to generate electricity so the building can consume that. Then you can start to optimize the cooling of that building. So you don't need to use the chillers all the time. You just use it when there's the right amount of people. If you zoom into a building and then look at the tenants, then you can start to optimize the lighting as well. You don't need to have all the lights on in your office all the time. Just have it when there's enough people there. And even for meeting rooms, I think we've all been in meeting rooms that have been freezing, but it doesn't need to be that way. You can pre-cool a meeting room, and then you can turn off appliances and people have gone. And it doesn't just apply for one building, so you can do that across multiple buildings. And this is the kind of work that we do in CLP to deploy a lot of these solutions to smart buildings. So from a utility, so going back to that equation of figuring out what's happening within the grid itself, in the past, this was the only device this was typically the device that a utility would have to understand consumer behavior. It's just a meter. So it wasn't too long ago where you would just have a meter where you would get a read of the customer's consumption once a month or once every 2 months. Very limited data points. Yes, smart meters are becoming a lot more prevalent, but still, it's not a lot of visibility. You get information every 5 minutes or every 30 minutes. Still, it's not as active as what you saw in that example. What a utility really needs to do is understand all these different types of devices that are connected to that grid. So it's a jungle of sensors that are out there, and a lot of these are smart solutions. That's all from a utility perspective. Now, if you think about from a customer perspective, customers are looking to be more sustainable. They want to optimize their buildings, their offices. But how does a customer decide and choose the right energy saving or energy efficiency solutions? So what we did at CLP Innovation is launch something called Smart Energy Connect. So it's a website where you can go to clpsec.com. And what we've done is curated all of these different energy saving solutions and then put it under one roof. And what we do with customers is go through a design process to see, well, how do you want to save energy? What are your targets? And we deploy these different types of IoT solutions there so we can help the customer save energy. But at the same time, we get visibility of how they're saving energy because typically these involve these IoT solutions where you can get visibility of what's happening on a minute-by-minute basis. So getting that data is really, really important. So when we thought about developing this framework, what we did was we first started from the data. So what are the types of data that we require? What are the types of information that a customer would need in order to get visibility to optimize their buildings. Secondly, we looked at, well, what are the types of applications and services? And then finally, what are the types of devices that we need to deploy? So although it was a very simple framework, it was really helpful for us to start in that order. Now, thinking about that, being a utility, what we typically would have done is to build this service is define a monolithic architecture and then go ahead, figure out the types of servers, infrastructure that are required, purchase the servers, setting it up in our data center, which makes a lot of sense for us. I mean, we're a utility. We own our own property. We generate our own electricity. However, it doesn't really help in this landscape because all these different types of smart solutions, energy-saving solutions, they evolve over time. So whatever we size from day one, it'll become obsolete very, very quickly, which is why we decided to not just choose public cloud services such as AWS, but we decided to choose native services. And that's really important for us because it really helped us optimize our operations. So some of the principles that we used when we were optimizing was, first, we wanted to make sure that we had the right DNA within the team. Because if you think about these IoT solutions, you need to make sure that these can be deployed and iterated over time. You test it, you trial it, you deploy it very quickly. So one of the other things we did was we made sure that we set up a DevOps culture to begin with, because we really wanted to focus on getting these outcomes to our customers as quickly as possible. In fact, our team structure with our technology team, we've only got about 20% of infrastructure resources, which is typically half what you see in an IT team within a utility itself. Secondly, what we did was we always made sure that we optimized, and we learned that the very, very hard way. So in one of our first deployments, we started to extract data from smart meters, about several million records. Within about a month, we got a bill of tens of thousands of dollars because of just the large volume of data. And the reason we did that was we didn't optimize very well. We chose just the first service that we saw, and then the data started streaming in, and you get the bill. But what we did was we shut that service very quickly. Within a week, we optimized that and then choose smaller services, which really helped, and we also adopted native services as well. The third key thing for us was going serverless. So instead of always deploying EC2 instances, our first port of call is to always use Lambda functions. Not just for us when we deploy our own applications, but even partners as well. So when we get partners that have an energy efficiency solution that want to work with us and go to market together, we also strongly encourage them to switch to Lambda. And that's helped us with cost savings. So we had one vendor that had a solution which was going to cost us about $3,500 a month to use. And switching to serverless, it dropped down to about $500. That was a great cost saving for all of us, but it also meant savings in our resources as well, because we don't have to spend time in managing the servers. We can focus on getting that service to our customers. So going back to this problem space of getting visibility on the grid, this is something we spent a lot of time on, and we actually wanted to share with you on how we think about the different AWS services we use in order to attack this problem. But first, rather than jump into architecture diagrams, we wanted to at least go through a simulation with you of a very simplified network. So here you see a network with solar, wind, electric vehicles, energy storage, but we wanted to do a short simulation with all of you where we create our own grid within this room with just 2 resources. But what I'll do is I'll pass over to Dee to go through that demonstration.
Okay, thank you, Bob. So in this simulation, I would like to invite all the audiences to participate. So we're gonna use your mobile phone and also your laptop, whichever can connect to the internet, to simulate today a simplified version of what we call an active grid. So just imagine each of your devices is one household. So within this household, you have your normal load, like from the morning. If we look at the picture, so from the morning you have a little peak at 7 and 8 a.m. because everybody waking up, and then it gradually cool down during the daytime because everyone go to work. And then you pick up again a little bit, the mini peak during 3 or 4 p.m. because the kids are coming home. And then at 7 or 8 p.m. when everybody's coming home, cooking dinner, watching TV, so you have another huge peak, and then gradually cool down over the night. So that's the normal household. And also, if you install something on your rooftop, with a solar panel, in a sunny day, your generation would be something like this. So you gradually pick up, and then probably going to peak at 1 or 2 p.m. in the afternoon, and then gradually cool down when the sun goes down. But to the grid, we want to visualize this in a more aggregated way. So you have to overlay those two loads together. And remember that your active load, which is the blue line, is something you consume from the grid. But the orange line is the generation that you actually feed back to the grid. So to the grid, we actually overlay those two layers together. We simply use the value of the blue line subtract the orange line, so you get this black line you see on the chart. So this is the real load that we see as a utility company that injected to the grid. So now I'm going to ask each of you if you can scan this barcode or simply log on to game.clpscp.com/client. You will see two buttons, something like this. So every click of each button will generate similarly a 1 kilowatt load to the grid. So we want to capture that data. So these two boxes here will show the aggregated clicks of both numbers. But it's not started yet. So after 5 seconds, this game will automatically stop, and we're going to chart all the clicks over the time through a line chart which I showed before. So I have to refresh this game, and then everyone can start to click. I want every one of you to click randomly. I don't want to, because in reality, the load and also the consumption, the generation are kind of random to us, so we cannot predict. So you can choose either click one button or both buttons at a random rate, or you can click them both at the same time. So I'm going to count to 3, and then we can start. Okay, 3, 2, 1. Let's start. So you can see the numbers coming in right now. Somehow I've run this demo for multiple times. The blue clicks are always more than the orange clicks. So if we chart this, I'm going to a chart. Oh, it's very nice. Something like this. So here you can see on the top, the blue line is the load. Imagine the household, this is what we consume from the grid. And the orange line is the power they generate from your household, injecting back to the grid. And as a utility company, the black line is actually the power we need to generate from the power plant. So traditionally, we only need to cater the blue line because that's what we do before. Now, with all the renewable energy that's injected into the grid, it actually will cause volatility to the grid power load. So what we can do is we can actually reduce the capacity of the power plant to generate less power, which is a good thing for us. But actually, if you are in a utility company, you know to turn on and turn off a power plant is a very expensive thing to do. So you can do some other things to remediate, like we can store the power using maybe battery pools, or you can pump the water to a reservoir high in the mountains, so when you need it, you can discharge the battery or release the water to generate power back on. So this game is just to demonstrate how easily that we can use cloud-native services to actually create a simple real-time app to simulate this simple power network. So let's look at the technology behind this mini demo. We just used two very simple cloud-native services. One is called the S3 bucket, Amazon Simple Storage Service. So we create two buckets. One hosts a static page each. So one is for the client, which is the two buttons that you see on your phone or on your laptop, and the other is the dashboard that we show on the screen. And then in order to connect those two pages together, we use an AWS service called AppSync. So judging from the name, you can predict that this service is actually used to synchronize data between the edge device and to the cloud. So actually you simply use AppSync to aggregate all the click numbers to the cloud, and then we display that in the dashboard in a real-time fashion. Of course, you can add a database behind this to capture all the data, but actually, since it's a very simple game, we only spend 1 day to develop this, so we don't bother even to capture the data. So this is the performance part. You can see we can use very simple services to handle real-time performance. But in real life, there are more problems that we need to tackle. Performance is just one thing. Security is also very important. It's actually the top one priority for all the utility services. And then storage, we want to capture all the data to put them into persistent storage, either for long-term or for short-term. And connectivity. We need consistency and reliable connectivity from the edge into the cloud so that you can always capture the data. And also monitoring. If something goes down or something not working, we should be notified and we need to know. So I'm going to use one of our applications that we developed last year. Actually, that's the first application we developed to offer to our customer. Because earlier last year, Hong Kong government offered the feed-in tariff scheme. Means everyone in Hong Kong, you can purchase renewable energy sources to install, say, rooftop solar on your rooftop, and then you generate power. And then government forces the utility company to buy back those power at a very high premium rate. So all of a sudden, there are many people request to store a solar panel on the rooftop, but all the apps comes with the OEM is more for engineering focus. So there are a lot of parameters only engineers understand, but for the customer, they only need to know how much power I'm generating and also how much money I'm making right now. So that's the thing that they care about. But actually, we did a little bit more, is that we also can generate some of the statistics, like the year-to-date, month-to-date generation, your aggregated generation. And also, based on the weather forecast, we can use some machine learning to predict your generation for the next day and also the next week. So first, we need to get the data from the client rooftop to the cloud. There are two options to do this. Option one, if the PV panel you purchase, specifically the PV inverter that comes with the Ethernet port, we can simply just use the Ethernet cable to connect that to a 3G router or 4G router. Then you can use the 3G router to establish a VPN connection to the cloud. So by doing that, you can actually use a Lambda function in the cloud that can query the inverter as if it's connected locally. So very convenient. But the downside of this, obviously, if the internet is broken or unstable, you're going to lose all the data, and you cannot retrieve this data back, because once it happens, it's gone. That's why we have the option 2, which actually we replace the 3G router with a little bit more expensive edge server. Although it's called a server, actually it's an ARM-based edge device. It's no bigger than your smartphone, and you can put some 3G chip there as well, so you can talk to the cloud. And within this server, you can install a Linux operating system, and then you can install a local database. You can run some script there to query the local device, and then you can cache the data in your local mini database. So in case the internet is broken, you can still synchronize the data to the cloud once the network is back on. So this one is a little bit more expensive, but it's more reliable. So once the data now all in the cloud, the other thing we want to do is we want to capture all those data. So the obvious choice is we use Amazon Kinesis data stream. So for the real-time data, like the one we showed just now, you want to see how much power you're generating right now, how much money I'm earning right now. You can just use a simple Lambda function to subscribe to the Kinesis data stream. So you can stream in the data to the client side. Whenever they open their phone, it can push the data to their phone. So this is the real-time, very simple. But also, you want to capture all those data. So there's one line I didn't draw here is everything that landed in Kinesis, we're going to use a Lambda function to actually sync all the data to S3 bucket, and then which we later ship to a data lake so we can do further analysis. But for this app, for this particular app, you can actually use a range of Lambda functions, like to do some calculation, year-to-date, month-to-date calculation. You can use your machine learning API to predict the next hour or the next 3 days prediction. And then you can store all this data in a persistent database. Here, the database we chose is called Graph database. It's one kind of a NoSQL database. Just like all other NoSQL databases, it's very good at handling real-time data and also very good at handling large volume data. And also we choose Graph database because its ability to handle very complex relationships, which I will drill down later. And then now we get all the data in the database. Very simple now, you can just write some Lambda function to query the database and then expose that through the API gateway. So whenever the clients, they want to refresh their app, they can grab the data from the database. And from client side, you want to authenticate the client. So the obvious choice, you use AWS Cognito. So the user is enter the username password, they get a security token to their phone, they use that token to query the content from the API gateway, which is further protected by web application firewall. So you can define certain firewall rules there to protect your application. Very simple setup. So you can see end to end, this entire architecture is just like playing a Lego. When you need some service, when you encounter a problem, you just grab some cloud-native services and plug in into the architecture. Plug in, plug out. So you can iterate your development lifecycle really quickly and really easily. And also because majority ignore the graph database part, because last year, I'd like to say we were limited by the technology of our time, so we have no choice to use a 3-node cluster. So besides that, all the other services are cloud native, so that you don't have to worry about the resiliency, the performance, also the maintenance, because AWS is going to handle that for you, so you can just focus on delivering the code and delivering the business value. And also, everything is pay as you go. So you don't have to set a scheduler to turn on, turn off the VM to save money, because it's all pay as you go. And because there are a lot of native services available, we just use Cognito and WAF. Actually, our entire AWS environment are protected by Guard Duty and Shield, so it can protect you from a general or known attack. So this is the current architecture. This is not perfect because we still have 3 nodes of EC2 instance running. So now we're actually running this new architecture in our lab environment. We're actually deploying this to some of our clients already. So there are 3 services we introduced. One is that, like we're playing Lego, we want to put a AWS IoT service between the edge and the Kinesis, so that we can gain more data and consistency services. And then we finally can get rid of the 3-node EC2 cluster. We can use a cloud-native graph database service called Neptune. The Neptune is an AWS-managed graph database service, so that we can just enjoy it like you enjoy Aurora and DynamoDB. And also you notice that we can actually get rid of the API gateway, and we replace it with a service called AWS AppSync, which is a service we use to develop our simple demo there. So AppSync is a cloud-native service that supports GraphQL, which will explain them one by one in detail. So the first one is the IoT. IoT actually is an entire category of service. It's not one service. So with the IoT, you can actually enjoy a lot of the services offered in this IoT ecosystem. So before we go to cloud native, this is our current setup for the deeper down connection from the edge to cloud. So if you look at the upper path, so on the edge side, we install a Linux operating system, and then you install Docker so that we can install a database and also Node.js, so that we can do the data. But also, in order to monitor the device, we actually install an agent called Telegraph. So the Telegraph actually sends telemetry to the cloud, and that comes with the Telegraph is a database called InfluxDB, which captures all this time series data, and then you can further analyze that in Grafana. I believe that's an open source tool many people use as well. So you can set up rules in Grafana, and then you can send the notifications to your Slack channel. So this is the upper health monitoring path. So for the data path, we actually use Node.js, and then you can store the data locally using MongoDB. So when the internet goes down, you can actually store data locally, and when the data goes up, you can run some logic to check the consistency, and then ship the missing data to the cloud. So in the cloud, you use Kinesis, as we mentioned before. One thing I want to mention that because you have to keep track of the devices you deployed, so we actually use a relational database table that is resetting Aurora to manually categorize all our IoT devices. So this is our existing setup. You can see there are 6 or 7 open source technologies here. So whenever there's an update, whenever there's a security patch, there's a lot of testing going on there. It's a huge hassle. And also, you spend a lot of time to learn how to use and how to integrate those open source technologies. That's why we're now evolving to this cloud native services. So on the edge side, we deploy AWS Greengrass. That it's a plugin that you can install on your edge operating system. So with Greengrass, the beauty of that is it's an extension of your AWS cloud. So all the Lambda functions you can run in your cloud, you can specifically designate that AWS Lambda to run on your edge device. So you can control the code remotely via AWS console. So on the Greengrass, there are a lot of cloud-native services you can enjoy. One thing is called a certificate. So you can download a certificate for each device. And the certificate can identify itself, and also it can make connection to the cloud, so that there's a corresponding service on the cloud. You can see it's called IoT Device Registry, because now you can discover all the devices you have been installed. So you don't have to use a database to manually count or manually track all the devices. So this is the identification part. And for the health check, there's a service called the Shadow. So you have one shadow on the edge side, and also you have another shadow on the cloud side. So those two will actually synchronize the edge status on its own via MQTT protocol, so that you don't have to worry about the synchronization of the status. And then when you get the device status in the cloud, you can run certain rules. Again, there's a rules engine provided natively in IoT service catalog, and then you can send notification to your email, to your mobile phone, or to your Slack channel via Amazon SNS service. For the data reading, as you can see, you can get rid of the local database and the Node.js, because now you can deploy Lambda to the edge and use the Lambda actually to read the data and send the data to the IoT core in the cloud. So the Lambda on the edge and the IoT core, they actually communicate with via MQTT. So the beauty of MQTT is that it can handle the offline data synchronization automatically. It means if the network is broken after several hours, after several days, when it comes back online, IoT core can figure out the data inconsistency and to synchronize the data by itself. So that for us, we don't have to write and maintain such complex logic on the edge. But still, you have the ability to use Lambda function in Greengrass to access your local, maybe some log files, and also you can store database there. You can do that, but in this particular application, we didn't do that. And then from IoT core, you can send the clean data to Kinesis, which consume later. So this is the IoT part. So next one I'm going to talk about is the Amazon Neptune. I want to do a quick survey, like how many people are using Graph database in production environment? Oh, we have one. Thank you. I'm a big fan of Graph database. Okay, the reason why we chose Graph database, one reason is obviously for the performance, because relational database, if your data volume increase, the query time really suffer. The other reason is because we're in the infrastructure or the utility industry. If you look at this simple diagram, so you have different nodes. Each node is an asset. It's a home. It's a power plant. It's a substation. It's a solar panel. And all those nodes are connected via power lines, physical power lines. And then we actually simulate what do we see, what do we feel in the physical world to the digital world using a graph model. So Graph database actually use node and edges, which is the relationship between this node to store information. So you can store data in both node and relationships. So you can map actually each node represent each physical asset or logical asset in the reality. And also you can capture the relationship by creating those edges or multiple edges between those nodes to capture the relationship. And that's why Graph database is also called a schemaless database, because we cannot predict what our customer are going to install, what kind of device they're going to install, or the topology of the network, because they change. And then, so similarly, we can change very naturally in our Graph database schema as well, because the schema is very fluid. The other beauty is that Graph database, when you traverse the graph, is actually traverse from one node and a hop through the relationship to another node. So when your data grow exponentially, if you use a relational database, if you do complex joins, the query time gonna grow exponentially. But with Graph database, your query time stays relatively consistent, no matter how big your data grow. And again, we can talk about this for a very long time. Today, we're talking about infrastructure, so I'm going to move on. So that's the graph database we choose. AWS, obviously, you handle everything, the heavy lifting to AWS, so you don't have to manage the OS, the data consistency, the high availability, all those are taken care of. The other service is AppSync. So actually, we use this in our demo. The AppSync is the AWS managed GraphQL service that can help you to synchronize data in real time. So before we use AppSync, I believe many of you use API Gateway, RESTful service. So this is how we used to get data from the cloud. So imagine the solar app again. You want to know the weather forecast because you want to know the weather for the future. So we purchase the weather forecast from a weather channel so you can query the weather data. And then you want to get real-time data, so you can Lambda to read from Kinesis, so you can push the data to your edge device. And also you want to know the year-to-day, month-to-day, the aggregated number, which is queried from a database, our database. And also you want to do some little bit of forecasting based on the weather data, and then you want to get that data as well. And then lastly, you want to get some customer master data, their name, their address. So there are 5 different endpoints, 5 different data sources because you follow microservice architecture. Whenever the user log into their phone, they click refresh, it actually go to those 5 different data points to grab the data in the predefined API format. So this is what we're doing now. So if we use AppSync, as you can see, first thing that we reduce the number of Lambda functions we need to manage because AppSync is a service that can aggregate all the backend different data sources together in one single point. And it actually provides the integration capability for some of the cloud-native services such as HTTPS or some database service such as Aurora, DynamoDB. You don't have to write Lambda function to do data mapping. You just do a configuration change to connect AppSync to the backend database so that you can query the data through AppSync. And the other beauty of that, you can see from the communication from your mobile device to the cloud, there's only one line because you can consolidate all the 5 different endpoints into one endpoint. So through this one endpoint, you can query the backend data through a language called GraphQL. So if you're not familiar with GraphQL, it's kind of similar to SQL. So you can specifically define which field you want to query. And also, you can add filters to each of those fields. So when you submit your query through this one endpoint, the cloud will return you the exact result you want, no more, no less. So this can dramatically reduce the traffic between your edge device and also the cloud, which can further to promote and improve your performance of the application. So this is GraphQL. And we have been using AWS actually since last year. Although we learn everything from scratch, we are learning a very hard way. So there are certain lessons we would like to share with you. Some of the things we like, some of the things that you need to watch out. So the first thing is the multi-tenant choices. Because with the cloud-native services, if you do a 3-tier application, so you can front-end, back-end, database, you have very flexible choice. You can actually run the load for each customer in separate Lambda instances, or you can just share them if you are lazy. And also, if the customer requires, you can actually store your data in different database instances, or you can consolidate them into one database instance. But for some extreme cases, you can actually spin up the entire VPC just for one customer because that customer requires. But those are no problem for us because everything now is in infrastructure as code. You can just use Terraform script to spin up the entire environment in a matter of hours. And the other beauty is that since everything is cloud native, everything is pay as you go. So we are charged by how much traffic are coming through the cloud. It's not by how many instances you spin up. So you can become very fluid in the multi-tenant choices. Well, the other benefit is it actually breaks the barrier between the development and the operation part. As perhaps mentioned that actually we only have 20% of our employees specifically dedicated to cloud computing, but actually every engineer in our tech team can write code because now cloud computing is actually writing code. So there are certain cases our cloud engineer helping some of the project writing the backend code, like the backend API, or some extreme cases actually starting to doing front-end development, which I don't want to see, but they can do that. So you naturally cultivate this DevOps culture, and you don't have to promote everything we do DevOps. You force people to learn, to go through courses. It will naturally happen if you go cloud native. And the other thing is that the evolving catalog. As I mentioned before, we use a lot of the open source technologies that we have to learn and maintain and manage and upgrade and do the patching. But with cloud native services, you can just get rid of those the open source that you run on your own. And then Amazon is really doing great on this because every time or every month you check, there's some new services available. And if they're not available, you can actually yell at your account manager, so they will listen and then they will report back. And sometime later, it might be available as well. There's some lessons learned about the watch out. Because you do cloud native architecture, cloud native service, it's good. It's very fast. It's very easy to use. But there are certain clients, they specifically require on-premise implementation, like government. So you need to think about, for every service that you consume in the cloud, you have to find a matching open source technology or some technology that you can run on your own. So our approach is that we actually find a containerized solution for each of the cloud native services we actually use. So whenever there's a client that wants to do on-premise implementation, you containerize each of the services, and then you just run the Kubernetes cluster on-premise. So you can bring this infrastructure to any cloud or any on-premise implementation. The other thing is called cold start. Well, there are many topics on the blog. The forum talking about cold start issue at the beginning. We're also facing similar issues. So when you first time log onto an app or a website, it seemingly takes a very long time to load, and then after that, everything is very quick. We thought it's a cold start, so we're thinking about you use a CloudWatch to ping each of the API on a regular basis to keep them warm. But actually, after investigation, we found out that most of the time, 99% of the time, is because your bad coding or bad configuration is actually not due to the infrastructure issue, especially when you are not using Java. By the way, we use JavaScript, so we shouldn't actually notice the cold start issue. So when you're actually facing some performance issue, investigate your code, investigate your configuration first before you spend money to ping each of the API on a regular basis, because that's really cost. The last thing is about the API governance or general governance, because now spinning up cloud services is so easy. All the developers, they can do on their own. So at the beginning of our development, we actually hit some of the limitations set by AWS. And then, again, we go back to investigate. We found out that it's all due to bad governance and also bad architecture. So if you plan well and architecture well, you shouldn't hit those ceilings. Especially now, AWS actually are raising the ceiling of each limitation year by year. So it's going to be very rare that you see this in your day-to-day development.
So to wrap up, what you saw was some of the principles that we followed. And we only had time to go through just one application, which was an application that looks at solar monitoring. But these principles we've followed for all of our different services which we've launched to our customers. So these include things like smart lighting solutions for large offices, a building analytics solution for an aged building where we can identify faults so that facility managers can go and focus their efforts rather than being reactive and react to complaints. So there's a lot more to our story. So on the next slide, we've got our contact details. We're here all week. Feel free to WhatsApp us, and we're happy to geek out about energy or cloud-native services. What's been really exciting for us was we looked at this problem of getting visibility for the grid, but then when we started engaging our customers, sustainability and energy saving was a lot more important. So it made a lot of sense for us to put our efforts there. So throughout the year, we have around 20 different services that we offer to customers. And on top of that, we've deployed a whole bunch, so the equivalent of where we manage around 2,000 devices, get about 20,000 data points, and we've identified energy savings, which are the equivalent of planting about 17,000 trees, which has made a lot of this very, very meaningful for us. So with that, I wanted to thank you for your time. We've got probably around 5-10 minutes for any questions that anyone has. Thank you.